All right, so now we are on, this is lecture 2, Thursday's lectures, and we're on 6.8, chapter 6.8, tidal streams and currents. So everything we've been talking about with this rise and fall of tides, we're talking about potential energy, in the vertical flow of water. So now we want to talk about, with talking about streams and currents, we're talking about the horizontal flow, which is the kinetic energy. So I know as the water flowing back and forth, if I have something out there to capture it, like we looked at the very beginning of chapter 6, if I can harness that energy going by, just in the current flowing, it's the same as having a, not a hydroelectric dam, but it would be the same as having like a paddle wheel or a turbine on a river. There's just that constant flow of water going by that I know is going to be there. Again, we can kind of go back to our figure 622, and we know there's going to be a current going, but now I can't do anything about these slack waters. When it's a slack water, it's a slack water because there's no capture. We know that these areas here are always going to be slack, and that's okay as long as you know that it's there. That's if I'm using tidal currents and tidal streams, right? Now what about ocean currents and ocean streams? How do they work? Any idea? Can you think of any ocean currents right offhand? Well, the big one that we deal with is the Gulf Stream. And the Gulf Stream is an ocean current. It varies by temperature, and I'm hoping that they have a map of it in here somewhere that actually shows how the Gulf Stream works. I'm going to take a guess at it, and we'll draw kind of a rough picture here of the United States, and there's Florida, comes up here is Maine, and then into Canada, and then up here we've got Greenland, and then over here we've got the UK, and we've got Europe. Down here we've got Cuba. We've got all these little islands and stuff, right? So down here in the Caribbean and down near the equator, which we'll call the equator down here somewhere, the water gets superheated, right? Water gets really warm. It flows up along the coast of the Atlantic, along the coast of the United States, comes up here, kind of makes a turn around Greenland, and this is all warm water going up. Now, from the polar ice cap and from Greenland, from the North Sea, I've got this cold water coming down. It hits this current and makes it turn and come south. So that flow is a clockwise flow starting in the Caribbean, comes up across by Greenland, all that cold water hits it and causes it to flow south. And it's fairly strong. We'll talk a little bit, we've talked a little bit about wind, and we can talk a little bit more. Actually, they're still talking about tidal. So we can capture, we know how to capture tidal currents because we just looked at that. We know how to, and that, it would assume that we know how to capture Gulf Stream currents as well, right? We should be able to. So if I just start like blocking this off, not really damming it or anything, but if I can get anywhere in here in the Gulf Stream and capture some of that energy as it goes by, we have the technology to do that. We should be able to do that, right? So we want to look at how could we do that? Where could we do that? So we're going to look at tidal currents compared to ocean currents first. Tidal current is just water flowing through a space. If you look at figure 628 on page 273, you have these restrictions right there where that tidal current flowing through a neck down area, in the same way that we looked at tidal barrages, that should be an ideal place for us to be able to capture that current. I have the entire Atlantic Ocean trying to push through the North Channel there in that little narrow space. So if I can get in there, there's a lot of energy, a lot of potential energy in that water because of all that water trying to be squeezed through a small space. Is naturally focused there by land. Those are the kind of places that we're looking at that would be ideal. You can see they have quite a few places there where would be ideal to be able to capture that. Of course, any of the narrows. So I'm guessing like up there in the Orkney Islands, the Shetland Islands, they're probably looking at a gap between the islands somewhere. It would not serve them well to just put it on the end of the end island for the water going by. But if I can put it between two islands where it's naturally forced through there, I'm going to get a whole lot more energy out of it. North Channel is a fairly obvious place. And it looks like they don't have it labeled. I don't know what the name of that is. Between the North Channel and the Bristol Channel, there's a point. Kind of sticks out right into the North Channel's flow. So I think they're probably capturing there that probably splits the flow of that current going through. So if they were to put something right on that point where it's split and being forced in two different directions, that's how they would capture that. Some of the potential of that, if you look at table 6.4, some of those, let's see, of course those names don't match up. I don't know what any of those mean. Oh, okay, they're there under that location. So the North Channel there, where we talked about where those, that might be ideal for us in between the two major islands there. The sites are potentially 0.9 and 0.8 terawatt hours per year. Pentland Firth, once again, that'd be between those islands. You can see the difference because of how narrow that is between those islands compared to the North Channel, and that energy being focused. You're looking at 1.5, 1.4 terawatt hours per year. So just capturing this, if you look at back to our drawing, if you look at the Gulf Stream out there, if I'm just capturing it there, it's not focused at all. It's a very broad, it might be 50 or 100 miles wide, and there's no focus there. There's no narrowing or anything that would increase the force in that area. You're just going to capture what is there. These natural features, by forcing it like that, you can see how much more energy there is. Where I looked at Bay of Fundy, let's see if we can't find that again, and we'll take a look at a tidal bore there, because that kind of let's see here. Now we were just looking at the rise and fall of that water. Let's see, expand my search here a little bit. This is called a tidal bore, and this one's on a supermoon, but you'll see where the tide is going against the current of the river. They're going in two opposite directions. So in this case, the tide is coming in towards us, towards the camera, and the river current is flowing outward. What that does is it causes the water to stand up. The water going out goes underneath, and the water coming in goes over the top and creates that wave. We have these in the United States. You'll see them in different places. Cook Inlet is a big one up in Alaska. It has one of those. On a smaller scale, you'll see them in Puget Sound. You'll see them in San Francisco Bay. You'll see them in large bays where there's a large fluctuation like that. There's two things to focus on there. Focus on the speed at which is coming in at. It's probably about the same as a river current, speed-wise. So that's something we could definitely capture, the speed of that. And where you look at where that turbulence is, where those two forces meet, that's the energies colliding. So all that disturbance you see is energy being dissipated. So we know that energy is there in the water. You can visually see it there. If we find a way to capture that energy, we have to picture what's involved there. So on page 274, there's a couple of things to notice there. Figure 629 talks about the shear effect of the water speed. Where is its speed at? And typically where the water moves is on the surface. The farther down you get, the less water movement there is. The water is much more still. It tends to stay in place. So the water that's moving as the tide goes in and out is that top, if we're looking at the Bay of Fundy and it's 45-foot tidal range, it's literally the top 50 or 60 feet that are moving, and the water below that is not. So it's something to keep in mind when we start talking about that design of, oh, that's cool, we'll just go out there where the Gulf Stream is. We'll put turbines down on the ocean floor in the Gulf Stream, and we'll capture all that energy. Well, the problem is the water is heated on the surface. So the water is moving on the surface with the Gulf Stream. If you go down very deep in the water's cold. I mean, you notice that when you dive in a lake. The water on top is really warm, and if you dive down towards the bottom, all of a sudden you'll hit that thermocline where, oh geez, it's cold. And that temperature never changes year round. Well, it's the warm water that's moving. So we have to think about that in that design, and 629 really shows us why that is. It's because of where the movement is. We want to capture the energy, and the only energy is where the movement is, which means it's on the surface, and we've got to figure out how to capture it as near the surface as we can. And then figure 630 is actually really cool in what we've been talking about, and the energy contained in water compared to wind or anywhere else. Um, it shows water speed in meters per second. Shauna, do you remember what we figured out for water speed was in the Clark Fork River? I think we figured it at about 1.5 to 2 meters per second, and that was in June. So it's actually still fairly fast during the practicum. End of June was between 1.5 and 2 meters per second. In order to, our y-axis is our extractable shaft power in kilowatts and our rotor diameter in meters. There's a kind of a size range where we're going to target what we would like. We're looking at mostly lower speeds, 1 to 2 meters per second based on 2 to 3 meters per second is what we're looking for in current speed. And we're looking at a rotor diameter of 15 meters. If I get a rotor diameter of 15 meters, that's about 500 kilowatts, which is pretty impressive because our little wind turbine out here is 1,000 watts at 26 miles per hour. And I'm trying to remember what that translates to meter per second, but it's pretty substantial. It's like 11.1 meters per second speed-wise, and that has a 3-meter diameter rotor to produce 1,000 watts. Here we're talking about producing 500 kilowatts with a 15-meter rotor diameter. So substantially more power in water than there is in wind, and your ability to capture it. But still, if you think about 15 meters is what, 50 some feet in diameter. So you're talking about fairly deep. You're talking about having to do this in fairly deep water. And you figure if there's ship traffic, you're going to have to be probably a rotor diameter below the surface at mean low tide. So you're going to need this to go in 100 feet of water at least in order to not be hit by shipping traffic or anything like that. And once again, now we need to look at, we go back from that, we look at, that's the size, expected size of the rotors, how big we think they're going to be, and then we go back to figure 629 and say, okay, where's the water moving at? So I either need them outside of the shipping channels or isolated in a way that there's no way a ship could run over them, or I'm going to capture less energy because they have to be down below the surface of the water. So it's a trade-off, and it's definitely something that you have to look at. Chapter 2 is kind of, paragraph 2 there on page 274 is kind of interesting. And I'll throw some of Brad's math in there for you just to torture you a little bit. The available energy is proportional to the square of the rotor blade length and the cube of the water velocity. So if we have even a small increase in the size of the blades or the water speed, because remember we're talking about cubed or squared, there's going to be a huge increase in capacity just by increasing either the rotor size or the water speed, the water velocity. So ideally, the way that relationship would work is we'd want to put the biggest possible blade diameter into the fastest current that we can find and just make crazy amounts of power, in theory. But there is obviously limits to that, both structurally, environmentally, the source of the energy of do you have a suitable location that can actually do that? Maybe, maybe not. If you can find somewhere there are places that have 10 meters per second current. Some of those little narrow, I'll tell you from sailing in the inside passage up through Canada and Alaska along the coast with all those islands, there are some places there that are really narrow that on a ship going 15 knots, which is about 20 miles an hour, to go through there, I could literally walk on the beach next to it faster than what the ship was going through that current in these places where it narrowed down between two islands. There are places you can get out and walk faster than what the ship was going, even though it was turning for 18 or 20 miles per hour. At the same time, structurally, what would you have to do to build something that would hold up to that kind of constant current? Would be brutal, be very hard on equipment. And typically we don't want that. I mean, typically we don't want surges. I don't want 11 knots of current and then in one direction and then 0 knots of current and then 11 knots of current in the opposite direction and then 0. We'd actually much rather find somewhere where we can just have 3 or 4 meters a second. That's really feasible. That's something we can work with and have it be more constant. That's kind of our goal there. And we talk about their advantages. Actually, I'm sorry, before I do that, one of the different or disadvantages of that compared to tidal barrage is tidal barrage is captured and I can focus it. If I basically I'm building a giant dam, I've captured all that water. The only way the water can get out is if it goes over my turbines. I'm not going to let it out any other way. It has to go past my turbines. It has to give up its energy so I can make electricity. If I did a tidal stream turbine where I've just got a big turbine sitting out there in that tidal stream, the water's free to go wherever it wants. It can go around it, it can go over it, it can go under it. I want to funnel it as best as I can, but realistically, it's just going to be on its own. And as a result, I have to have a much larger system because I can't control it. It has to be a much larger system in order to capture the same amount of energy. But the advantage is that thing's running on both the ebb and the flood tides, and it's running 100% or it's not running 100% because the speeds are going to vary, but as long as there's a current going by, it's spinning. Right. So that other than the slack tides, there is no dead spot on it. So it has a much higher capacity factor than a tidal barrage. So we lose some control, but it's effective for more hours of the day. Slightly less efficient because we're not funneling it, but I can build it bigger to do the same thing. So there's ways around it. So we got some issues. Talks about the other issues in there, and you guys talk about wave energy in chapter 8. But for now, just talking about anything that you put on the ocean. It's highly corrosive, so we're dealing with corrosion. Anytime you put metal in the ocean, it's called galvanic action or electrolysis. You have something moving through salt water. It causes an electrical charge, and that electrical charge will actually erode the metal. It pits it and erodes it and eventually destroys it. And that's a problem with ships, and they use zinc anodes on there. It's a sacrificial anode, so the electricity attacks that zinc, which is softer, instead of the steel. But even then, you still have damage. So you've got that. You've got sea growth that's going to grow on this thing, even though it's moving parts. This thing's going to have to be cleaned off because every little critter with a shell is going to want to latch onto that thing and call it home.
Right.
So eventually those things build up enough that the thing won't function anymore. The blades won't spin, or, you know, it won't be able to rotate like it's supposed to. So there's going to have to be some maintenance on it for that. You're going to have problems with fishing nets getting into it. You're going to have, how do I get my power to shore? Now I got to look at transmission lines. Transmission lines underwater are subject to much more extreme conditions than the transmission lines on shore. So they're much larger, and pretty much anything larger costs you more money. We got to worry about boats going by, obviously. Wildlife. Yeah, so there are going to be some environmental things. The one cool part about it that I really like, that I think is an advantage, is there's no visual impact. And if people can't see it, they don't know that it's there. They tend to not think about it. If I put a wind turbine up on top of the M up here, everybody driving in town that looks at the M, their eyes are going to be drawn up to the wind turbine. People that like wind turbines are cool with that. People that don't like wind turbines, it's just poking at them. Every time they see it, it just makes them a little bit madder. So there is an advantage to some of these technologies being out of sight. Of people they're not as bothered by them because they can't see them, and they can't see any of the impacts. And that's one of the things that doesn't necessarily talk too much about this. The other downside is, what is that environmental impact that we don't see? As those blades are spinning around, if I put in a turbine, or even if it looks like a wind turbine, you know, so there's a fairly large gap between the blades and stuff, are we going to be chopping up fish? Are we going to be chopping up humpback whales? Are we going to be chopping up sea turtles? I don't know. It's not going to be as obvious. There's not going to be a dead turtle laying on the ground next to the wind turbine. But, you know, whereas we walk out there and you can see a dead eagle laying next to a wind turbine, potentially, you're not going to see the results of this. But I have no doubt that there would be some environmental impact from this. And that would be something to keep in mind. So some of the things they're looking at in the UK for doing that. I like the idea of the 6.31 is pretty low tech, but very doable. You have a buoy as your buoyancy that actually holds your unit up in the current, which is nice because you can adjust that to maximize your current. And then it has a mooring cable going to an anchor. And the reason I say that I like this is the serviceability of this is I can pick up this entire unit, put it on a barge, do my maintenance. I can clean it and get all the little critters growing on it off.
There's not as much material to clean.
Yeah, there's not as much material to clean. It's going to be some chains, and then the actual turbine rotor and generator unit. Everything else, you know, just sits there and it's not really doing anything. So that's a fairly easy one to maintain, and it might be good because it is portable and I can move it around and I can find the best place for it. And then you look on the next page, figure 632, there's one that's built on a pylon, and that's kind of ingenious. I do like that. The fact that they can just raise it up out of the water to do the maintenance on it.
Yeah.
So it's probably on hydraulics. The other advantage of that now is I can move that thing up and down to maximize. We talked about from that last figure, was it 629? Yeah, figure 629, where is the current the strongest at between the top and the bottom? Well, you know what, I can vary this height to maximize where my blades are, and I can maximize it at any given time according to the stage of the tide. So whether it's high tide or low tide, I can always be maximizing that thing and always adjust looking for the strongest current. The downside of that is going to be structurally. If I've got these big blades out here on long arms, the leverage is pretty strong. I guess the two of them opposite of each other kind of counteract each other, but their overall sail area pushing in one direction or another on that piling's got to be pretty substantial to stand up against that. And if you look at that right above the blades where they're raised up on the left-hand side, you can see a little dude down there just above that hub.
Oh, how funny, there he is.
So you can see that
Those are huge.
those things are huge. I mean, that piling's probably, if you figure let's just throw it out there that he's 6 feet tall. I mean, that piling's 12 feet in diameter at least, if not bigger, and it's gonna have to be way down deep and anchored very solidly into the bottom, probably braced and everything else. So structurally, that is not a small structure. That is a pretty good sized unit. But conversely, one of the cool things is looking at that tower, you can see the current going past it, flowing from left to right. That's a fairly substantial current going by there. And if you start looking at buildings in the background too, that kind of gives you a sense of scale as well of how big that thing is.
Yeah, those are some pretty good-sized houses back there.
Let's see, that one is in Northern Ireland. It was in 2008. 1.2 megawatt capacity, and that's at 2.4 meters a second. So it's about half the capacity of one of the large wind turbines out of Judith Gap. But if you look at that, even though we look at that, we're like, wow, that's really huge compared to that guy. It's not really when you compare it to the size of those wind turbines out of Judith Gap. That's pretty small comparatively. Rotors are 16 meters in diameter. And that's cool. It doesn't have to actually swivel around because the pitch can be rotated 180 degrees so they can capture both the ebb and the flood tides. So that one's fairly relatively low power, but they said the successors are expected to be capable of 2 megawatts with rotors up to 20 meters in diameter. So getting considerably larger. That's cool. So they're looking to build a 10 megawatt tidal farm array using several machines off the coast of Wales, a similar project off the Isle of Skye in Scotland. And then they're looking at a 100 megawatt project off of Northern Ireland. Should be initially the first 50 megawatts should be available by 2018, and a 2020 completion date for another 100 megawatt project. So it's rolling, it's happening. Kind of cool, just as a thought drill, just something to think about, that you can try anything, and see if it works. Who knows? That one in figure 633 at the bottom of page 278, the Stingray, is a hydroplane and just oscillates up and down, just kind of does the wave motion.
Reminds me of the airplane fan.
Yeah, that's exactly what it is. It's a wing, and as it goes up and down, it's moving hydraulics, and those hydraulics spin a shaft, which spins a generator.
It's totally submerged, isn't it?
What's that?
It's completely underwater, but still
Yes.
on the surface.
Yeah, it's underwater, but near the surface. And some of the advantages of that is fewer moving parts. And the less moving parts you have, the less potential for problems you have. And sometimes simple is the easiest way to do it. That's why I really had a lot of fun with the wave generation. You guys will get to later on. Is pretty cool. And a lot of it's similar to that Stingray tidal generator. Is it something that's jointed, looks like a giant worm out there, and as it bends, it moves hydraulics, and that hydraulic fluid spins a turbine, or spins a generator. So it shows there the advantage of that is you can run it in shallower water because it's got a limited motion up and down versus a rotor that has to have, it has 360 degrees. This thing I can control how much it moves up and down, so it's going to work better in shallow water.
You really didn't see that, you didn't know it was there.
Yeah.
Driving down the highway, you didn't know.
But and then they bring up though an interesting point that is kind of cool there in the third paragraph. So one of the things you got to look at it though, is reciprocating devices operate most efficiently in mid-stroke. So as it's on its upstroke or its downstroke, that's where the most energy is. But they slow down at the end of each one because they have to change direction, right? So it goes up and it stops and then it's coming back down. So there's no real energy at the top of that stroke, the bottom of that stroke. Just like the engine in your car. If you had a one piston engine, it would really be a pain in your car. It would be really annoying because you'd be able to feel those pulses at the top and the bottom of the crankshaft stroke, where the piston's at the top of its stroke and at the bottom of its stroke. Make for a very jerky ride. Well, we make an engine 4 cylinders or 6 cylinders or 8 cylinders, and that smooths that out so that you don't feel all those pulses. Well, this thing works the same way. So it's going to lose a lot of energy when it's in that step of the cycle, whereas a rotor is not losing that. Talking about using a ducted rotor there on 635. We talked about how if we can capture it as it's forced between two islands, that's great because it narrows it down and increases the force. Well, they're looking at doing the same thing, only using basically a funnel on the outside of their turbine, so it captures more. Then figure 636, a vertical axis ducted rotor. And then you got the hydrofoil 634. There's two of them that are opposing each other. There's a seesaw. There's all kinds of neat different ways to look at things. And like I said, it's one of those things that you just, we look at it as like, hey, that's pretty novel, but sometimes you got to think outside the box and look at these ways. That might be where the next breakthrough is. So I'm going to leave off right there. We'll call that a day, and we will pick this back up on Tuesday. Don't forget your summary 3 is due on, is that due on Tuesday? I don't want to, let me pull that up to make sure I'm not telling you wrong. Nope, your exam is next week. But I believe, yeah, I think the cutoff, summary 3.
I think it's technically due today, but late by Tuesday.
No, it's due Tuesday, next Tuesday
But late by
at 2 o'clock. So by now, like I said, you should have all your information gathered up, all your data. It's just a matter of making the charts. Check out Brad's videos on Moodle from last week that show you step by step how to do it. And again, if you have any questions, shoot Brad or I an email or swing by the office, come talk to us. We'll be more than happy to help you with it. So with that, we will see you next Tuesday.